I'm getting a series of polylogarithms. So here's an integral from 0 to 1 of polylogarithm base p of x, polylogarithm base q of x divided by x dx. So how do we solve this integral? First of all, just to simplify things, we will use the definition of polylogarithms. We know that polylogarithm base p of x is just the sum from n equals to 1 to infinity of x to the power n by n to the power p. We'll use this definition, and that will make things somehow simpler, though not really, but somehow. Okay, and we have integral from 0 to 1 by x. Yeah, and now we know that the first LIP is sum from n equals to 1 to infinity x to the power n by n to the power p, and LIQ is sum from k equals to 1 to infinity x to the power k by k to the power q. So we have used the sum definition of polylogarithms. Yeah, and now from the denominator convergence theorem we can like swap the sum in integrals. Yeah, let's take the sum outside and integrals inside. And this thing is like normally used in most of the places, just to simplify things. So after doing that, we can see that now this is double sum and then integral from 0 to 1 of x to the power n plus k minus 1 by n to the power p k to the power q dx. Yeah. After that, now it's just a simple integral of power. Yeah. We have sum from n equals to 1 to infinity, sum from k equals to 1 to infinity x to the power n plus k by n plus k. Yeah, and we also have other items like n to the power p, k to the power q in denominator, and this is all from 0 to 1. Yeah, now we substitute 1 and 0 for x and then see what do we get. Sum from n equals to 1 to infinity, sum from k equals to 1 to infinity, this is 1 by n plus k, n to the power p, and k to the power q. Yeah, and at 0 this is just 0. So now let's make a change. Let's swap the sums. First of all, let's write the sum from k equals to 1 to infinity, and then let us write 1 by k to the power q. Yeah, because this will be constant for the world of n. And then sum from n equals to 1 to infinity, 1 by n to the power p, n plus k. Yeah, this sum over here, like this can be simplified in, yeah, but first of all, let us just name this sum. Let us just name this sum in the following way. Let's by this symbol for p comma k. Yeah, this function is defined as sum from n equals to 1 to infinity 1 by n to the power p n plus k. Let us define this sum in this way. Yeah, and we will try to find the value of this sum. Yeah, that will not be too hard. I'll show you how. And after we find that, this result will just be sum from k equals to 1 to infinity of the symbol we have, which we have put again written symbol, and p comma k by k to the power q. Yeah, and again we can find this, and that will be our answer. Yeah, just to simplify things, we are doing it step by step. First of all, we will find this function, and then we will solve for the sum when the function is divided by k to the power q and is summed over infinity. Okay, now let's go over this. Let's go over this function. Now, something to notice is when p is 1, this function actually simplifies. Yeah, so if p is 1, in that case this function is actually sum from n equals to 1 to infinity of 1 by n times n plus k. Now if you use partial fractions, you will see that this is actually 1 by k sum from n equals to 1 to infinity 1 by n minus 1 by n plus k. Yeah, and now we know that this sum over here, sum from n equals to 1 to infinity of 1 by n minus 1 by n plus k, this is exactly the nth, or sorry, kth harmonic number. This is exactly the kth harmonic number. Now we have a by k over here. So you see that it nicely simplifies to kth harmonic number divided by k. Yeah. So we see that the case per p equals to 1 is simpler. But now let's try to see how we can solve it for general p. Yeah. So we'll basically try to break this into a lot of partial fractions. Yeah, we can try to do that as well, but instead of breaking it into a lot of partial fractions at once, we can also use recurrence and do it step by step. So let me show you how can we do it step by step. So for that we can use you can use similar logic. Let's say we can write it as n to the power p minus 1. We know that just n remains over here, n plus k remains, and we can now see that we can break it into 1 by n minus 1 by n plus k, and all of this is divided by 1 by k. Yeah. Now we see that if we basically write it as two sums, 1 by k, sum from n equals to 1 to infinity of 1 by n to the power p minus 1 by k, sum from n equals to 1 to infinity of 1 by n to the power p minus 1 n plus k. And now we know that this is just the Riemann zeta function of p. Yeah, so we have Riemann zeta of p by k minus 1 by k. Now this is just our beloved function with input p minus 1 and k. So this is the function of p minus 1 comma k. That's good. Yeah, so now we have got a recurrence relation between the function of p comma k and p minus 1 comma k. Now we can use this to find other terms as well up to 1. Yeah, and per 1 we know what it's going to be. So now the function of p comma k will be, first of all, Riemann zeta of p by k minus 1 by k. Similarly, here it will be Riemann zeta of p minus 1 by k minus 1 by k, the function of p minus 2 comma k. Yes, and we can proceed in similar manner. And at last, okay, so let me write the terms first. P minus 1 by k. Also notice that the signs are changing. Minus minus, now it will be plus 1 by k square of p minus 2 comma k. Okay, now let me try to write all the terms. Yeah. Riemann zeta of p by k minus Riemann zeta of, so this is basically the function of p comma k. Okay, Riemann zeta of p minus 1 by k. Now similarly, notice that whatever number is subtracted, the same thing is here actually, is it? Wait a second. It's k square over here, not just k. It's k square, also it's k square. Again, whatever number is subtracted, like one more is here. Yeah. So basically, over here, if it was Riemann zeta of p minus 2, we will have k cube. Yeah. Similarly, if it was minus Riemann zeta of p minus 3, we will have k to the power 4. Please note this in mind. Yeah. And we know that now please note that if in place of 2 we have p minus 1. Yeah, so basically these signs are like governed by this number itself. Whenever it's 2, here's a negative sign. Okay, I think here it's a plus. Sorry. Okay, so whenever there's a even number, there's a plus sign. When there's odd number, there's minus sign. Basically, sign is governed by this number itself. Yeah, and to have this number as 1, we need to have in place of this 2 or these numbers, we need to have p minus 1. Yeah, and corresponding to the this p minus 1, here's also same number. So basically, from this we can observe that if this goes on, our last term will be basically 1 by k to the power alpha minus 1 The sign is also governed by alpha minus 1, and when it's alpha minus 1, we have the function of 1 comma k. Yeah, can you make sure of this thing? And similarly, the second last term, let's also write second last term. Basically, the second last term, so there are many terms in between them. Second last term will also have the sign minus 1 to the power alpha minus 2. Yeah, and note that so whenever if there is 2, there is 3 over here. Yeah, so first term, in the first term we had p minus 1, p minus 2. Yeah, so in the second term we have 1, in the third term we have 2, in the fourth term we have 3. Now this over here is actually the alpha minus 1th term. Yeah, now this is alpha minus 2th term, is it? So that's why in alpha minus 2th term we will basically have Riemann zeta of 2 by k to the power alpha minus 1. Yeah, so basically what I mean to say is, so basically this is the first term, this is the second term, this is the third term, fourth term. Yeah, and it goes on. Yeah, and also over here it starts with 0 and then 1 and then 2. Yeah, and in the last one we have 1 comma k, and over here this is actually second last term, so we have alpha minus 1. Yeah, in second last term, so basically if it's 2, there's a 1 less over here. So if it's over here it's alpha minus 1, so here that will be alpha minus 2, and alpha basically this is not alpha, this is basically p. Sorry for that. This is basically p. How did I get alpha? This is p, this is p, this over here will also be p, this over here will also be p. Yeah, this is p minus 1th term, so we have p minus 1, but over here it's always 1 less. Yeah, so p minus 1 less is p minus 2, that's why we have 2 over here. I think now it's clear. And also over here similar thing, but here in place of alpha I need to write p, and then it all makes sense. Now it makes sense. Okay, so now it makes sense, and now let's try this in sum notation. We have sum from basically n equals to 1 to this is p minus 1. Yeah, and in denominator we just have k to the power n itself. Yeah, just k 1 2 3 up to p minus 1, and in numerator we basically have minus 1. Yeah, and then for the sign we need to have okay, so basically this is p minus 1, so here 1 less, that means n minus 1. Yeah, and next here also, here we basically have minus 1 minus 2. In second term we have minus 1, that means what we can do is Riemann zeta of p. So in second term if we subtract minus n, it will be minus 2, but we just need minus 1, so we can make plus 1. This generalizes to other terms as well. Yeah, so and for last thing we have minus 1 to the power p minus 1, k to the power p minus 1 by the function of 1 comma k, and we know that the function of 1 comma k is just as k by k. Okay, so we finally have this nice formula for the function p comma k, and now the problem is gonna be a lot easier after this. After this we just have few steps and then we will close the problem. So now we have that sum from n equals to 1 to p minus 1 minus 1 to the power n minus 1 Riemann zeta of p minus n plus 1 by k to the power n plus minus 1 to the power p minus 1 as k kth harmonic number by k to the power p. So now what we need to do, we basically need to divide this by k to the power q and sum over k equals to 1 to infinity. Yeah, I think that that will be the answer. So let's divide this by k to the power q. If we divide this by k to the power q, we have, sum from n equals to 1 to p minus 1, yeah, minus 1 to the power n minus 1 Riemann zeta of p minus n plus 1 by k to the power n plus q. Now here also it's minus 1 to the power p minus 1 as kth harmonic number by k to the power p plus q. Now let's sum this from k equals to 1 to infinity. If we sum all of this from k equals to 1 to infinity, we basically get sum from k equals to 1 to infinity of the function of p comma k by k to the power q. And here all of the terms are independent of basically k, and this only one term is in k, and we know that here's the k is raised to some power, and if k goes from 1 to infinity, this is just Riemann zeta of n plus q. We can clearly notice that, and that's pretty obvious. We have minus 1 to the power n minus 1 Riemann zeta of p minus n plus 1 Riemann zeta of n plus q. And over here we see that to sum this up, we just need the classical Euler formula. And that closes all the matters, and that does the things. So if you just use the classical Euler formula, we see that this will nicely reduce to the formula, which I will just state over here. Sum from k equals to 1 to infinity the function of p comma k by k to the power q, and over here it's sum from n equals to 1 to infinity, 1 to p minus 1 minus 1 to the power n minus 1 Riemann zeta of p minus n plus 1 Riemann zeta of n plus q. Yeah, and from classical Euler formula we have this thing as, okay, so firstly we have 1 plus p plus q by 2, yeah, and then after that we will have Riemann zeta function, yeah. So after that let me take the classical formula. Okay, after that we basically have Riemann zeta function of q plus 1, so that means p plus q plus 1, yeah, and then minus 1 by 2, so in the same bracket sum from k equals to 1 to p plus q minus 2, yeah. So basically this number over 2, and then this number plus 1, okay, and this number minus 2 over here, and then we will basically have the Riemann zeta of k plus 1 and then Riemann zeta of p plus q minus k, and the big bracket closes. So this is finally our answer, and let me write it in proper way. Yeah, so this actually is known to be our integral from 0 to 1 lip of x liq of x by x dx, yeah, and this equals to basically sum from n equals to 1 to p minus 1 minus 1 to the power n minus 1 Riemann zeta of p minus n plus 1 Riemann zeta of n plus q, and then plus minus 1 to the power p minus 1, yeah, always multiply with this thing, so 1 plus p plus q by 2 Riemann zeta of p plus q plus 1, yeah, and then we have minus 1 by 2, take this alternating sign inside the sum from k equals to 1 to p plus q minus 2 minus 1 to the power p minus 1 Riemann zeta of k plus 1, is it k plus 1? Yes, and then Riemann zeta of p plus q minus k, Let me check if this is correct or not, since it's long expression and we have nearly completed the solution. Yeah. Mm, the answer is the answer is basically sum from n equals to 1 to p minus 1 remains zeta of, okay, so mention p minus 1 remains zeta of p minus n plus 1 n plus q, and then plus minus 1 to the power p minus 1 1 plus p plus q by 2 remains zeta of p plus q plus 1 minus 1 by 2. Sum from k equals to 1 to p plus q minus 2 remains zeta of k plus 1 minus 1 to the power p minus 1, and then remains zeta of p plus q minus k. Yeah, that's the correct answer, and I hope you understood the solution. If you have to talk about the flow of the problem, we just took it to the sum notation first of all, using the definition of the polylogarithm function, and then we introduce the function, we try to find its properties, and we try to evaluate it as an infinite sum. Yeah, that's basically a long sum. Then divided that expression by k to the power q, and then summed it up, where we had to use classical Euler formula, and that nicely gave us the answer. So this was it. This was an interesting journey of problem solving. Hope you enjoyed the solution. Thanks for watching, and look forward to seeing the upcoming videos too.